Hello and welcome to week 5, lecture 2. We're going to talk about conservation of momentum. This is from chapter 6-4, and we're going to talk about conservation of momentum and then do sample problem 6-4. So we're going to walk through this situation where we have two masses in motion relative to each other, and they're going to collide. But this is before the collision. So we have our masses, we have the momentum of each of them given by these vectors. And we're defining our system to be these two masses. The system, just these guys. And we're assuming our system is isolated from the environment with no external forces acting during the collision. And we can use vector addition to get the total initial momentum of our system before the collision. The textbook does it this way, where it puts the tails of both of the vectors together, and then the vector sum is kind of like projected out from there. We can do it either way. We can do it this way, where we have, here's our initial momentum vector of 1 and momentum vector of 2, and then the vector sum of them is this. Either way works. So the total momentum of the system is given by capital P, and it's just the sum of momentum of 1 plus the momentum of 2. And we can take the derivative of the total momentum with respect to time. So remember, when you take the derivative of a vector, it just distributes the derivative to all the parts. And from last week, we found that the derivative of momentum with respect to time is force. So we end up with the sum of forces acting on each of the masses. But part of our setup with defining this as our system was that no forces were acting on these objects before or after the collision. So it would be 0 before and after the collision, but what about during? So during the collision, remember, the masses exert equal and opposite forces on each other, so that's kind of an action-reaction pair of forces that goes on during the collision. So that means that the sum of forces of one will equal a negative sum of forces of the other one. So this is also 0. So it's 0 both before, after, and during the collision. And if a time derivative of an object is 0, then that object or that variable is constant. So this is telling us that the total momentum of the system, of this isolated system, is constant. So again, we have our total momentum is the momentum of each object added together. And we have found that the time derivative of the total momentum is 0, which tells us that the total momentum is constant. And that also means that the final momentum of the system equals the initial momentum of the system. And this is the concept of conservation of momentum. So when the net external force on a system is 0, the total linear momentum of the system is constant. So we can, and I'll show you with an example in a moment, but we can use what we know about the initial momentum of the system to find out information about the final momentum of the system, specifically because the total initial momentum equals the total final momentum, or just in general, the total momentum of the system is constant. So we're going to do this sample problem. We have a man of mass 65 kilograms running along a pier at a speed of 4.9 meters per second. He jumps from the pier into a rowboat of mass 88 kilograms that is drifting without friction in the same direction at a speed of 1.2 meters per second. And we want to know that when the man is seated in the rowboat, what is the final velocity? Okay, so I drew the situation. We have our man running along the pier at 4.9 meters per second, and then the boat is moving in the same direction at 1.2 meters per second. And then we want to know what the final velocity of the man and boat is. So let's write some of our stuff down. Mass of the man is 65 kilograms. Mass of the boat is 88 kilograms. Velocity initial of the man is 4.9 meters per second I hat, just so that we keep track of that. Initial velocity of the boat is 1.2 meters per second, also an I hat or positive X direction. So what we just covered is that the concept of the total momentum of the system, and so we'll call this one initial, which is the initial momentum of both parts of the system, in this case, the man and the boat. And we'll find these values for the momentum to get ourselves a number or a value for the initial momentum of the system. So the initial momentum of the man is the man's mass times his initial velocity. That is 65 kilograms times 4.9 meters per second, which is 318.5 kilogram meters per second. And then the initial momentum of the boat, mass of the boat, initial velocity of the boat. That equals 88 kilograms times 1.2 meters per second. And this is 105.6 kilogram meters per second. So the initial momentum of the system is just the sum of those two, which gets 424 kilogram meters per second I hat. So that's the initial momentum of the system. And we just covered that if it's an isolated system with no external forces acting, which it is in this example, that the initial momentum of the system equals the final momentum of the system. And the final momentum is given by the mass of the man times the final velocity, and they're both moving together, so they're moving with the same final velocity, so also the mass of the boat times the final velocity, but we can write this as the sum of their masses times the final velocity. And so that tells us that the final momentum of the system is the masses times the final velocity of the system. And we also know, though, like we just said, that the initial momentum of the system equals the final momentum of the system. So this is also equal to the initial momentum. And we want this final velocity, so we can just divide the sum of those masses on both sides, and we get this equation, which is the total momentum divided by the total masses. And we can plug in our numbers. So the total momentum initial, which is also the total momentum final, is 424 kilogram meters per second divided by 65 kilograms plus 88 kilograms. Plus 88 kilograms. And that gives us a final velocity of 2.8 meters per second for our system, but also individually too. So again, how we think about these problems is finding the momentum for each object, in this case, the man and the boat. And then we were able to find the initial momentum of the system. And because momentum is conserved in isolated systems without external forces acting, the initial and final momentum of the system are equal. And we can use that to find the final velocity. In this situation, the man and the boat are moving together after the collision. And so, yeah, we were able to use our information of the initial momentum to find the final velocity of the system. Okay, that's everything for this one, a little bit shorter. Yeah, have a great day.